Hello everyone. This chapter I'll talk about technical principles of Hbase. After this course, we'll be able to know system architecture, key features, basic functions, and some enhanced features of Hbase. First, let's take a look at the introduction to Hbase. Hbase is a column-based distributed database built on top of the HDFS, which means that Hbase uses HDFS as its file storage system with high reliability, performance, and scalability. I'll explain column-based later. Hbase is actually similar to Google's Big Table, designed to provide quick random access to huge amounts of structured data. So in the same way, we can use Hbase to store and process big table data, which has billions of rows and millions of columns. And it also provides real-time read or write access to data in HDFS. Also, Hbase uses Zookeeper as the collaboration service. So in short, Hbase is the Hadoop database, a distributed, scalable big data store. We know that Oracle, MySQL, and many common databases are actually relational database, RDB for short. But Hbase is NoSQL, not only SQL, which usually refers to non-relational databases. Most common ones are MongoDB, Redis. So let's take a look at the difference between them. Hbase is distributed, which is easy to understand because it's built on top of HDFS, and it's column-oriented. What is column-oriented? Normally, in a table, in Oracle or MySQL, data is stored by rows. Data can be added, modified, or read by row. But when we need all data in the name column, we may need to read the entire row to get the data. So in this case, we may read some unnecessary data. That's why we find another way to store data, which is by column. Data can be read or calculated by column, but when a row is read, we need multiple I/O operations. So in Hbase, data is stored by column. This is what we call column-based. It's different from relational databases. Let's go back to see other differences. Here, relational database has fixed data structure. What does it mean? For example, we have a table with employee data. The columns include ID, name, phone, and address, and the attributes of each column are all fixed. So we need to predefine the data structure before we put actual values into the table. However, Hbase doesn't need to. We can make dynamic extension of columns. For example, an employee table in Hbase. For first record, we have ID and name. For second record, we have ID, name, and phone. For third record, we have ID, name, and address. Each record could have different columns. Columns can be dynamically extended. Also, Hbase supports common commercial hardware, which costs less when making expansion, while the expansion of RDB costs much more. And the relational databases are I/O intensive. So these are the differences between them. As for the application scenarios of Hbase, it can be used whenever we need to provide fast random access to massive data, or we need high throughput, or we need to process structured and unstructured data, like text files, images, videos, web pages at the same time. Or we do not require the ACID features of traditional relational database, which are atomicity, consistency, isolation, and durability. They are a set of properties that ensure normal database transactions. Atomicity requires that each transaction be all or nothing. If one part of the transaction fails, then the entire transaction fails. Consistency means that, for example, consistency determines that A plus B equals 10. If a transaction changed the value of A, B must also be changed. Isolation ensures that two or more transactions will not be executed in an interleaved manner because this may cause data inconsistency. Durability means that after a transaction is executed successfully, modifications made on the database are retained permanently. No rollback is performed unless necessary. When we don't require any of these four features, we can use Hbase. Infusion inside Hadoop, Hbase is a basic component for storing massive data. It's a column-based distributed storage system built on top of HDFS. And there are cases that Hive and Spark depend on Hbase for upper layer analysis. Take a look at the storage mechanism. How data is actually stored in Hbase. Well, data model in Hbase is key value, which means data is stored in the form of key value pairs. Key is used to quickly query a data record, and value is used to store user data. But each key corresponds to many values. Like in Huawei, everyone has an ID number. We can take this as a key, which can correspond to name, age, phone, address, and many other information. But when we use the ID number to quickly query, how to make sure we get the name value, not the age? That's why key value must store some description of itself, such as timestamp and type information. This requires some structure space. RDBs predefine the data structure in the database as a series of tables containing fields with well-defined data types. In contrast, key value systems treat the data as a single opaque collection, which may have different fields for every record. This offers considerable flexibility and more closely follows modern concepts like object-oriented programming. Because optional values are not represented by placeholders as in most RDBs, key value storage often uses far less memory to store the same database, which can lead to large performance gains in certain workloads. Here, keys are implemented as byte arrays and are sorted in byte lexicographical order, with the lowest order appearing first in a table, which simply means that the keys are sorted byte by byte from left to right. So after key is ordered, data subregions will be created based on the row key range. Each subregion is a basic distributed storage unit stored in different nodes. And key value pair has specific format, which contains key information such as timestamp and type, 7 parts in total. The same key can be associated with multiple values, so we can use these 7 parts to distinguish different values corresponding to the same key. Like each key value has a column qualifier. There also can be multiple values associated with the same row key and column qualifier. We know that data in Hbase can be updated, so there may be multiple versions of the same data record. In this case, they are distinguished using timestamp. Here remember that Hbase will return the latest version when querying without specifying the timestamp. Column family consists of one or more columns. A column is a label under the column family. Then let's see the functions and architecture of Hbase. Hbase consists of the following parts. Hmaster involves the active Hmaster and standby Hmaster in HA mode. Active Hmaster manages region servers in Hbase, including the create, delete, modify, and query of a table, balances the load of region servers, adjusts the distribution of regions, splits regions and distributes regions after they are split, and migrates regions after a region server failed. And standby Hmaster takes over services when the active one fails. The original active Hmaster serves as the standby Hmaster when the fault is rectified. Region server provides read and write services of table data as a data processing and computing unit in Hbase. Region server is usually deployed together with the data node of the HDFS cluster to perform data storage. Client communicates with Hmaster and region server by Hbase RPC mechanism. The client communicates with Hmaster for management and communicates with region server for data operation. And Zookeeper provides distributed coordination services for processes in Hbase cluster. Each region server is registered with Zookeeper so that the active Hmaster can obtain the health status of each region server. HDFS provides highly reliable file storage services for Hbase. Almost all Hbase data is stored in HDFS. Inside of a region server, there are the following 5 components: store, memstore, store file, hfile, and hlog. A region consists of one or multiple stores. Each store corresponds to a column family, and the store contains one memstore. Data inserted to a region by client is cached to the memstore. When the memstore capacity reaches the upper limit, region server flash data to the memstore to HDFS. As more data is inserted, multiple store files are generated in a store. When the number of store files reaches the upper limit, region server merges multiple store files into a big store file. Hfile defines the storage format of store files in a file system. Hfile is actually the underlying implementation of store file in Hbase, and hlog prevents data loss when a region server fails. Multiple regions in a region server share the same hlog. Hmaster manages region server in Hbase, include create, delete, modify, and query of a table, balances the load of region server, adjusts the distribution of region, splits region and distributes region after it's split, and migrates region after region server expires. Hmaster is in active standby mode. A cluster can have 2 Hmaster processes. When the cluster starts, the processes compete for being the active Hmaster. There is only one active Hmaster, and the standby Hmaster process is in the waiting status and does not involve in cluster transactions when the cluster is running. Region server provides read-write services of table data as a data processing and computing unit in Hbase. The region server is usually deployed with the data node of HDFS cluster to store data. All reading and writing requests of user data are handled based on interaction among regions on region servers, and regions can be migrated between region servers. In Hbase, A data table is divided into subtables based on the range of key value to implement distributed storage. A subtable is called a region, which is the most basic distributed storage unit in Hbase. Each region is associated with a key value range, which is described using a start key and an end key. For example like this, region 1 has the start key row 001 and end key row 010. Each region only needs to record a start key because its end key serves as the start key of the next region. There are two types of regions, meta region and user region. Meta region records the routing information of every user region. The address of meta region is stored in the root table in Zookeeper, and the address of user region is stored in the meta table. Column family is a physical storage unit of a region. A table consists of one or multiple column families horizontally. A column family can consist of multiple random columns. A column is a label under the column family, which can be added as required when data is written. The column family supports dynamic expansion, so the number and type of columns do not need to be predefined. Columns of a table in Hbase are sparsely distributed. The number and type of columns in different rows can be different. And Zookeeper provides distributed coordination services for processes in Hbase cluster. Each region server is registered with Zookeeper so that active Hmaster can obtain the health status of each region server. The metadata table is a special Hbase table, which is used by the client to locate a region. Metadata table includes Hbase meta that records region information of user tables, such as region location and start and end row keys. Besides, the metadata table is split into multiple regions, and the metadata information of region is stored in Zookeeper. Next, let's take a look at key processes of Hbase. Hbase can be compared to a library. You can think region server as a floor in the library, and region is the books of a certain type. So books of the same type are stored in the same region. For example, you can think the first floor as a region server. So inside of it, there are multiple regions. Each one includes a certain type of books. Like books about general biology are stored in region 1, and books about environmental biology are stored in region 2. So when users write data into Hbase, first, the client initiates a request. This process is like a book supplier sends books to a library. But which floor the books should be sent to? That is to say, which region server and region should data be sent to? In order to determine that, the Hbase client connects to Zookeeper to obtain information about the region server where the Hbase metatable is located. The Hbase metatable records information about each user region, including the range of row key and the region server where the region resides. Based on the metatable, we can locate the region server of the region to which data is to be written. After obtaining all this information, data needs to be grouped. Data group includes two steps. First, get the information of region and the region server of tables based on the metatable. That is, find the location of each region in region server, and then transfer data to specific region according to row key. Data on each region server is sent at the same time. And then the Hbase client connects to region server where the region of the user table is located and issues a data operation command to the region server. The region server executes the command to write data into region. To improve data processing efficiency, the Hbase client caches region information of the Hbase metatable and user table in memory. When an application initiates a data operation, the Hbase client queries the region information from the memory first. If no match is found in memory, the Hbase client performs the preceding operations to obtain region information of the Hbase metatable and the user table. In either of the following scenarios, a flash operation of memstore will be triggered. Flash is a process to persist data from memory to disk. Once flashing the memstore of the whole region flashes. That's why the number of column families should not be too many. As time passes by, the number of each file increases because service data flows to the Hbase cluster. More files need to be opened for the same query, so the query latency increases. So in order to solve this problem, Hbase will automatically pick some smaller H files and rewrite them into fewer big ones. This process is called compaction, which can reduce the number of H files in a column family in a region and increase reading performance. There are two kinds of compaction, major and minor. Minor compaction reduces the number of storage files by rewriting some smaller files into fewer but larger ones. And the major compaction merges and rewrites all the H files in a region to one H file per column family, and in the process drops deleted or expired cells. This improves read performance. However, since major compaction rewrites all the files, lots of disk I/O and network traffic might occur during the process. This is called write amplification. Major compactions can be scheduled to run automatically. Due to write amplification, major compactions are usually scheduled for weekends or evenings. A major compaction also makes any data files that were remote due to server failure or load balancing local to the region. This figure shows more directly about the difference between minor compaction and major compaction. Minor compaction involves partial H files, while the major compaction involves all the H files. And notice that if the data size of the region exceeds the predefined threshold, a region will split into two subregions. During this process, the reading and writing services will be suspended for a short time. The reading process of Hbase is kind of similar to the writing process. A client first initiates a reading request, which is like query of books in the library using a client. In this case, if the book code is specified, which is like a row key in Hbase, this is a GET request, which is an accurate search. If a code range is specified, this is a SCAN request, which is a query by range. Then, to locate the region based on the metatable. After After locating the corresponding region server and region of row keys, open a scanner to search for data. Because a region contains mem stores and edge files that include data, there are two types of scanner to read data in mem stores and edge files respectively. The scanner corresponding to edge file is store file scanner, and the scanner corresponding to mem store is mem store scanner. Users can get some future conditions to return the data that matches the specified conditions. There are some typical filter types like row filter, single column value filter, key-only filter, and filter list. And Bloom filter is used to quickly check whether a piece of user data exists in a large dataset. Notice that if Bloom filter returns the result that data does not exist, then this result is absolutely accurate. If it returns exist, there may be misjudgment. And data relative with Bloom filter in Hbase is actually stored in H files. At last, let's take a look at some enhanced features of Hbase in Fusion Insight HD. While Hbase is a distributed storage database of the key value type, data of a table is sorted in the alphabetic order based on row keys. If you query data based on specific row key or scan data in the scale of a specified row key, Hbase can quickly locate the data that needs to be read, enhancing the efficiency. However, in most actual scenarios, you need to query the data of which the column value is a certain one. Hbase provides the future feature to query data with a specific column value. All data is scanned in the order of row key, and then data is matched with a specific column value until the required data is found. The future feature scans some unnecessary data to obtain the required data. Based on the preceding description, the future feature cannot meet the requirements of the frequent query with high performance standards. To solve this problem, the Hbase secondary index is generated. It enables Hbase to query data based on specific column values. Take a look at this table. When the secondary index is not used, the mobile field needs to be matched in the entire table by row to search for specified mobile numbers such as 6854912, which results in long time delay. But when the secondary index is used, the index table is searched first to identify the location of the mobile number, which narrows down the search scope and reduces time delay. Hbase file stream, which is HFS, is an independent Hbase file storage module. It's used in Fusion Insight HD upper layer applications by encapsulating Hbase and HDFS interfaces to provide these upper layer applications with functions such as file storage, read, and delete. In the Hadoop ecosystem, the HDFS and Hbase face tough problems in massive file storage in some scenarios, like if massive small files are stored in HDFS, Nemnode will have great pressure, or some large files cannot be directly stored in Hbase due to Hbase interfaces and internal mechanism. The HFS is developed for the mixed storage of massive small files and some large files in the Hadoop. Simply speaking, massive small files and some large files need to be stored in Hbase tables. In the actual application scenario, data in various sizes needs to be stored. For example, image data and documents. Data whose size is smaller than 10 MB can be stored in Hbase. Hbase can yield the best read and write performance for data whose size is smaller than 100 KB. If the size of data is stored in Hbase is greater than 100 KB or even reaches 10 MB, and the same number of data files are inserted, the total data amount is large, causing frequent compaction and split, high CPU consumption, high disk I/O frequency, and low performance. MOB data is stored in a file system in H file format and save the address and size information about H files to the store of Hbase as values. This greatly decreases the compaction and split frequency in Hbase and improves performance. In this figure, MOB indicates the mob store that is stored on H region. Mob store stores keys and values. When reading data, mob store uses its own scanner to read key value data objects and uses address and data size information in the value to obtain target data from the file system. So this chapter mainly talks about Hbase, including key value storage model, technical architecture, reading and writing process, and some enhanced features of Fusion inside Hbase. Okay, that's all for Hbase. Thank you. Hello everyone, this chapter will talk about technical principles of Hive. We all know that the size of datasets being used for every industry is growing rapidly. Hadoop was the solution for large data storage, but using Hadoop was not easy for end users. Hive is an easy way to work with data stored in HDFS. Basically, you can just think Hive as SQL for Hadoop clusters. So after this course, we'll be able to know Hive application scenarios and basic principles, enhanced features of Fusion inside Hive, and some common Hive SQL statements. First, let's take a look at the introduction to Hive. So Hive is an open-source data warehouse system on top of HDFS that adds structure to the data. It can support PB-level distributed data query and management. It also provides the following functions: flexible ETL, supporting computing engines such as MapReduce, TAS. TAS here is an application framework which allows for a complex DAG of tasks for processing data, and Spark, direct access to HDFS files and Hbase, and is easy to use and program. Here, one more thing to notice. Some of you may be confused about data warehouse and database. Data warehouse is a system used for reporting and data analysis. Generally refers to the combination of many different databases across an entire enterprise. It usually stores historical data so that all of the relevant data may be used for analysis. Database is an organized collection of data. Data from various sources are collected into a single place. This place is the database. It usually stores current data for querying. The main difference between them is that database is used for online transactional processing, while data warehouse is designed for online analytical processing to analyze questions that are critical for your business. Consider the scenario where a bank ATM has disbursed cash to a customer, but was unable to record this event in the bank record. If this started happening frequently, the bank wouldn't stay in business for too long. So the banking system is designed to make sure that every transaction gets recorded within the time you stand in front of the ATM machine. These records form a database, but suddenly your manager asks for a report about maybe customer group for financial products. You cannot analyze the problem based on the database because it changes due to various updates. That's why we need a data warehouse where we can extract historical data from different sources and make analysis for specific problems. Hive is built on Hadoop for static batch processing. Hadoop has low latency and consumes a large number of resources during job submission and scheduling. Hive does not support quick query of data in a large-scale dataset. For example, querying data in hundreds of Hbase datasets has minutes of delay. Therefore, Hive is inapplicable for scenarios where it require low latency. For example, online transaction processing. So in actual application, Hive can be used for data mining, non-real-time analysis, data aggregation, and data warehouse. More specifically, Hive can be used for user behavior analysis or interest analysis. Hive does not support real-time query. We can use Hive for network log analysis, text analysis, and also some report analysis. In Fusion inside Hadoop, at the bottom is HDFS and Hbase, which are used to store the datasets. Then is Yarn that manages and schedules resources for applications. MapReduce, Spark, Taz are distributed parallel computing engines. On the top is Hive, a platform used to develop HQL like SQL scripts to do MapReduce operations by default. All Hive data is stored in HDFS. And here is the comparison between Hive and traditional data warehouses. They are compared from the following aspects. For storage, we know that Hive is based on HDFS, so it's infinitely scalable, but traditional data warehouses are of limited storage capacity. Hive can take MapReduce or Taz or Spark as the execution engine, while traditional data warehouses use algorithms with higher efficiency to query data. They are also compared from usage, flexibility, analysis speed, index, usability, and so on. Hive has some advantages. For example, Hive Server, which is a process for Hive to provide external SQL services in cluster mode, Dual Metastore, which provides metadata information, and a query retry after timeout, make sure high reliability and tolerance of Hive. It uses SQL-like query. We can define functions and storage formats, and Hive also have multiple interfaces, like Beeline, JDBC, Thrift, Python, and OTBC. But Hive also has some disadvantages. To be more specific, Hive uses MapReduce as execution engine by default, so it has high latency. And Hive doesn't support materialized fields. Data updating, insertion, and deletion cannot be performed on fields. Besides, Hive is inapplicable to OLTP, which is online transactional processing. We cannot add, update, and delete column-level data. And last one is that Hive does not support storage process, but supports logical processing using user-defined functions. Storage procedure is similar to UDF. To save time and memory, extensive or complex processing that requires execution of several SQL statements can be saved into storage procedure, and all applications call the procedure. The major difference between storage procedure and UDF is that UDF can be used like any other expression within SQL statements, whereas storage procedure must be invoked using call statement. Okay, next, let's take a look at the structure of Hive. Let's look at the core part of Hive, driver. It manages the life cycle of HQL execution and participates in the entire Hive task. Driver is composed of three parts to break down the Hive query statements: compiler, optimizer, and executor. By default, compiler is used for compiling HQL statements into graph of map and reduce tasks. These tasks are interdependent. As for optimizer, there are logical optimizers and physical optimizers to optimize HQL execution plans and MapReduce tasks respectively. And executor is used for executing map and reduce tasks based on task dependencies. So driver is the most important part of Hive, the core of Hive. Also, we have metastore, which stores metadata of tables, columns, and partitions. Driver can connect with metastore to get any information about data if it needs. While Hive is a data warehouse infrastructure software that can create interaction between user and HDFS. The user interfaces that Hive supports are Hive command line, Hive Web UI, JDBC, and ODBC. Users can use command line interface to directly connect with Hive. And Web UI is a visual structure on Hive used for interaction with data, but users cannot directly use JDBC or ODBC to interact with driver. We need a Thrift server, which provides Thrift interfaces as the servers of JDBC and ODBC, and integrates Hive and other applications. In Fusion Insight Header, Hive contains the following components: Hive Server, Metastore, and Web HCAT. Hive Server provides Hive database services externally, translates HQL statements submitted by users into related YARN tasks or HDFS operations to complete data extraction, conversion, and analysis. And multiple Hive servers can be deployed in a cluster in load sharing mode. Metastore provides Hive metadata services as well as reads, writes, maintains, and modifies the structure and attributes of Hive tables. Metastore also provides Thrift interfaces for Hive Server, Spark, WebHCat, and other Metastore clients to access and operate metadata. Multiple Metastores can be deployed in a cluster in load sharing mode. WebHCat provides REST interfaces and uses them to run the Hive command to submit MapReduce tasks. Multiple WebHCats can be deployed in a cluster in load sharing mode. As shown in the figure below, developers make HTTP requests to access Hadoop MapReduce, Pig, Hive, HCatalog DDL from within applications. Data and code used by this API are maintained in HDFS. HCatalog DDL commands are executed directly when requested. MapReduce, Pig, and Hive jobs are placed in a queue by web HCAS servers and can be monitored for process or stopped as required. Developers specify a location in HDFS into which peak, Hive, and MapReduce results should be placed. Note that the current version does not support peak interface. In the order of granularity, Hive data is organized into database, table, bucket, and partition. Database is used to avoid naming conflicts for tables, fields, partitions, columns, and so on, and can also be used to enforce security for a user or group of users. If the database is not specified when a table is created, the default database is used. And tables are homogeneous units of data which have the same schema. A table corresponds to a directory in HDFS physically. Hive organizes tables into partitions, a way of dividing a table into coarse-grained parts based on the value of a partition column, such as a date. Using partitions can make it faster to do queries on slices of the data. To take an example where partitions are commonly used, imagine log files where each record includes a timestamp. If we partitioned by date, then records for the same date would be stored in the same partition. The advantage to this schema is that queries that are restricted to a particular date or a set of dates can be answered much more efficiently because they only need to scan the files in the partitions that the query pertains to. Notice that partitioning doesn't preclude more wide-ranging queries. It is still feasible to query the entire dataset across many partitions. A table may be partitioned in multiple dimensions. For example, in addition to partitioning logs by date, we might also sub-partition each date partition by country to permit efficient queries by location. A partition corresponds to a subdirectory of the directory where a table resides, and tables or partitions may be subdivided further into buckets based on the value of a hash function of some column of the table to give extra structure to the data that may be used for more efficient queries. For example, bucketing by user ID means we can quickly evaluate a user-based query by running it on a randomized sample of the total set of users. A bucket corresponds to a file under the path where a table or partition resides. There are two reasons why you might want to organize your tables or partitions into buckets. The first is to enable more efficient queries. Bucketing imposes extra structure on the table, which Hive can take advantage of when performing certain queries. In particular, a join of two tables that are bucketed on the same columns, which include the join columns, can be efficiently implemented as a map-side join. The second reason to bucket a table is to make sampling more efficient. When working with large datasets, it's very convenient to try out queries on a fraction of your dataset while you are in the process of developing or refining them. We'll see how to do efficient sampling at this end of the section. Note that it's not necessary for tables to be partitioned or bucketed, but these abstractions allow the system to prune large quantities of data during query processing, resulting in faster query execution. There are two types of tables in Hive: managed table and external table. When you create a table in Hive, by default, Hive will manage the data, which means that Hive moves the data into its warehouse directory. Alternatively, you may create an external table, which tells Hive to refer to the data that is at an existing location outside the warehouse directory. The difference between the two table types is seen in the create or load and drop semantics. Let's consider a managed table first. When you create or load data into a managed table, it's moved into Hive's warehouse directory. If the table is later dropped, the table including its metadata and its data is deleted. It bears repeating that since the initial load performed a move operation and the drop performed a delete operation, the data no longer exists anymore. This is what it means for Hive to manage the data. An external table behaves differently. You control the creation and deletion of the data. The location of the external data is specified at the table creation time. With the external keyword, Hive knows that it's not managing the data, so it doesn't move it to its warehouse directory. Indeed, it doesn't even check whether the external location exists at the time it's defined. It's a useful feature because it means you can create the data lazily after creating the table. When you drop an external table, Hive will leave the data untouched and only delete the metadata. But how to choose which type of table to use? In most cases, there is not much difference between these two. So it's just a matter of preference. Well, in general, if you are doing all your processing with Hive, then use managed tables. But if you wish to use Hive and other tools on the same dataset, then use external tables. A common pattern is to use an external table to access an initial dataset stored in HDFS. Then use a Hive transform to move the data into a managed Hive table. This works the other way around too. An external table can be used to export data from Hive or other applications to use. Hive provides multiple built-in functions, such as mathematical function, data function, and string function. If built-in functions are not enough for users, Hive also supports self-defined functions. Based on Hive provided by the Hive open source community, Hive Infusion Inside HD has a lot of features that customized for enterprises, such as co-location table creation, colon encryption, and syntax enhancement. HDFS co-location is the data location control function provided by the Hadoop distributed file system. The HDFS co-location interface is used to store associated data or data on which associated operations are performed on the same storage node. Hive supports the HDFS co-location function when Hive tables are created. After the locator information is set for table files, data files or related tables are stored on the same storage node to ensure convenient and efficient data computing among associated tables. And this is a command for how to implement Hive co-location. First, use HDFS interface to create group ID and locator ID, for example, and then create tables with specific group ID and locator ID. Here notice that you must use the insert statement to import data to this type of table to make the HDFS co-location feature take effect. And file format can only be text file and RC file, which is record columnar file. Hive also supports encryption of one or multiple columns in a table. When creating a Hive table, you can specify the columns to be encrypted and encryption algorithm. When data is inserted into the table using the insert statement, the related columns are encrypted. Hive column encryption does not support the field and Hive over Hbase scenarios. Hive supports two common encryption algorithms currently, AES and SMS4. Here shows an example of encrypting the phone column and the address column using the AES algorithm. Due to limitations of underlying storage systems, Hive does not support deleting a single piece of table data. But Fusion Insight HD Hive supports deleting a single piece of Hbase table data. Using specific statements like this, Hive can delete one or multiple pieces of data from an Hbase table that matches the expression. And with the controlling traffic feature, users can control the following things by configuring these parameters in Fusion Insight Manager. Why add this feature? Because there are too many requests of clients, it may cause the restart of the client. So Fusion Insight Hive supports to control the connection of users. In most cases, a carriage return character is used as the row delimiter in Hive tables stored in text files. That is, the carriage return character is used as the terminator of a row using query. However, some data files are delimited by special characters other than a carriage return character. Fusion Insight Hive allows you to use different characters or character combinations to delimit rows of Hive text data. Look at these steps. User needs to set the input format and output format first when creating a table, and then specify the delimiter in this way. So with all these features, Fusion Insight Hive is better than the community version in reliability, tolerance, scalability, and performance. Then let's take a look at some basic operations of Hive. While HQL is the query language of Hive, which is very similar to SQL, and also includes three types: data definition language, data manipulation language, and data query language. Here makes a few examples of Hive basic operations. First is to create a managed table. If not exists, is used to create a table if the table doesn't exist. Example employee is the table name, and then give the field name, type, and a comment, which is optional. This line specifies the row delimiter as comma and stored as a text file. And the difference of creating an external table is to add external here and also specify the storage location. This statement is to modify the column after the date in company column into money with string type and this comment. To add columns to an existing table, given the table name, the column name, and its type. This statement is to change the file format into a text file, and you can delete some records of a table given the condition. After using the job statement, the table doesn't exist anymore. This statement is to list columns and column types of a table, and this one will show the statement of how to create this table. And here are some commands for how to load data, import or export data. Notice that when data is imported to a Hive table, a data validity check is not performed. It's only performed when data is read. Where is used to give query conditions, and group by means to divide a dataset into several small datasets based on certain rules, and data process is performed on the small datasets. Data can be grouped by using the aggregation function. Union all is used to combine result sets of two or more select statements. The result set can contain the same value. We can join two tables with the same column, and when a query item is the condition of another query item, this is called subquery. So this chapter mainly talks about Hive, like its basic principles, application scenarios, enhanced features in Fusion Insight, and also some common Hive SQL statements. Okay, that's all for Hive. Thank you. Hello everyone, this chapter will focus on technical principles of streaming. After this course, we'll be able to know real-time stream processing, system architecture and key features of streaming, and also some basic CQL concepts. First, let's take a look at the introduction to streaming. Streaming is a distributed real-time computing framework based on the open source Storm. In simple terms, it's a distributed framework for real-time processing of big data, like Apache Hadoop is a distributed framework for batch processing. Streaming makes it easy to reliably process unbounded streams of data, doing for real-time processing what Hadoop did for batch processing. It works on task parallelism principle, wherein the same code is executed on multiple nodes with different input data. It's simple, can be used with any programming language, and it's a lot of fun to use. Streaming has the following features. It performs data refresh and end-to-end delivery response in seconds or minutes, depends upon the problem. It has very low latency, and when processing data with streaming, unlike Hadoop, it computes data before persisting to disk, which ensures low latency. Besides, streaming supports continuous query and return the results to the client in time. And it's unbelievably fast because it has enormous power of processing data. It can keep up the performance even under the increasing load by adding resources linearly, which means highly scalable. It can be applied to a wide variety of use cases, like real-time analysis, online machine learning, continuous computation, ETL, and more. Let me make a few examples of open-source Storm. Many companies are using Storm as an integral part of their system, like Twitter. Twitter is using Apache Storm for its range of publisher analytics products. Publisher analytics products process each and every tweet and clicks in the Twitter platform. Apache Storm is deeply integrated with Twitter infrastructure. There is another example. Navisite is using Storm for event log monitoring or auditing system. Every log generated in the system will go through the Storm. Storm will check the message against the configured set of regular expression, and if there is a match, then that particular message will be saved to the database. In Fusion Insight, streaming is a computing framework for real-time processing. Streaming does not have any state managing capabilities. It instead uses Zookeeper to manage its cluster state, such as message acknowledgements, processing status, and so on. This enables streaming to start right from where it left, even after the restart. Compared with Spark streaming, while Spark streaming works an unbounded string of data, like streaming does, but Spark streaming is actually a micro-batch processing tool. Spark streaming is built on top of Spark, and it needs to represent the incoming flow of data within a stream as a batch in order to operate. So Spark streaming won't be able to support the low latencies. In application scenarios, streaming is suitable for cases that strictly require low latency, usually milliseconds, while Spark streaming is suitable for cases with less demanding of low latency, usually seconds. Before I introduce the architecture of streaming, let me show some basic concepts. Topology is the overall calculation, represented visually as a network of spouts and bolts. Think of a simple linear graph with some nodes connected by directed edges. Now imagine that each one of these nodes represents a single process or computation, and each edge represents the result of one computation being passed as input to the next computation. A streaming topology is a graph of computation where the nodes represent some individual computations, and the edges represent the data being passed between nodes. We then feed data into this graph of computation in order to achieve some goal. Nimbus is a master node of streaming cluster. All other nodes in the cluster are called as worker nodes. Master node is responsible for distributing data among all the worker nodes, assigning tasks to worker nodes, and monitoring failures. The nodes that follow instructions given by the Nimbus are called as supervisors. A supervisor has multiple worker processes, and it governs worker processes to complete the tasks assigned by the Nimbus. A worker will execute tasks related to a specific topology. A worker will not run a task by itself. Instead, it creates executors and asks them to perform a particular task. A worker process will have multiple executors. Spout is the source of stream. Generally, streaming accepts input data from raw data sources like Twitter Streaming API, Apache Kafka QE, and so on. Otherwise, you can write spouts to read data from data sources. Bolt is a component to process input streams and produce output streams. Bolts can perform the operations of filtering, aggregation, joining, interacting with data sources, and databases. Each spout or bolt executes as many tasks across the cluster. Each task corresponds to one thread of execution, and string groupings define how to send tuples from one set of tasks to another set of tasks. Tuple is the main data structure in streaming. It's a list of ordered elements. By default, a tuple supports all data types. Generally, it's modeled as a set of comma-separated values and passed to a streaming cluster. Stream is an unordered sequence of tuples. Zookeeper is a service used by a cluster to coordinate between themselves. Nimbus is stateless, so it depends on Zookeeper to monitor the working node status. Zookeeper helps the supervisor to interact with the Nimbus. It's responsible to maintain the state of Nimbus and supervisor. Then let's take a look at the architecture of streaming. First, client submits service topologies to Nimbus. Nimbus receives tasks submitted by the client, assigns them to supervisor. and monitors the status. Supervisor monitors and receives tasks assigned by Nimbus and starts worker processes that it manages. Worker processes run component processing logic. Each worker is a JVM process. An executor is the thread that runs specific service logic, and Zookeeper provides distributed collaboration services for service processes. Nimbus, supervisor, and worker register their information in Zookeeper. This enables Nimbus to detect the health status of all roles. Then let me explain some concepts in detail. A topology is a real-time application running on the streaming platform. It's a DAG composed of components. A topology can concurrently run on multiple machines. Each machine runs a part of the DAG. A topology is similar to a MapReduce job. The difference is that topology is a resident program. Once started, a topology cannot stop unless it's manually terminated. Spout is the message source of streaming. Generally, it reads data from an external data source and sends the data to a topology. For example, Spout can read messages from a Kafka queue and sends them as a stream, and Bolt can receive multiple input streams. After some processing, some bolts may send new streams. Complex string conversion operations, such as generating hot topics from Weibo messages, may involve multiple steps and thus require multiple bolts. Bolt can run functions, filter tuples, aggregate and merge data, and access databases. String grouping specifies what streams can be accepted by Bolt as input streams, and defines how to assign a stream to multiple tasks in a Bolt. A worker is a physical processing in running state in a topology. Each worker is a JVM process. Each topology may be executed by multiple workers. Each worker executes a logic subset of the topology. An executor is nothing but a single thread spawned by a worker process, and an executor runs one or more tasks, but only for a specific spout or a bolt. A task performs actual data processing, so it's either a spout or a bolt. A topology contains one or more workers that run concurrently on several servers. Therefore, a worker process is a topology subprocess, and a worker belongs only to a topology. A worker contains one or more executors, and each component has at least one executor. Therefore, an executor is a component execution subprocess, and an executor belongs only to a component. Tasks are specific processing logic objects. An executor thread can execute one or more tasks, but it only executes one task by default. Tasks are usually regarded as execution threads, but this is not true. The number of tasks indicates the maximum concurrency. The number of tasks in a component does not change, but the number of executors change. When the number of tasks is larger than that of executor, the number of executors indicates the actual concurrency. The concurrency of spout or bolt is the number of tasks in spout and bolt. In the preceding figure, there are two tasks in spout. This figure shows a topology, or we can say DAG, consisting of a spout and three bolts, and the nodes on each part indicate tasks, and the lines between tasks indicate streams. But what about this one? What's streaming group? We know by now that a stream is an unbounded sequence of tuples. between a spout and bolt or two bolts. Part of defining a topology is specifying for each bolt which streams it should receive as input. A string grouping defines how that stream should be partitioned among the bolt's tasks. That is to say, a string grouping defines how the tuples are sent between instances of those spouts and bolts. There are 8 built-in string groupings in streaming. For fields grouping, the string is partitioned by the fields specified in the grouping. For example, if the string is grouped by the user ID field, tuples with the same user ID will always go to the same task, but tuples with different user IDs may go to different tasks. For global grouping, the entire stream goes to a single one of the bolt tasks. Specifically, it goes to the task with the lowest ID. For shuffle grouping, tuples are randomly distributed across the bolt tasks in a way such that each bolt is guaranteed to get an equal number of tuples. For local or shuffle grouping, if the target bolt has one or more tasks in the same worker process, tuples will be shuffled to just those in-process tasks. Otherwise, this acts like a normal shuffle grouping. For all grouping, the stream is replicated across all the both tasks, using this grouping with care. For direct grouping, this is a special kind of grouping. A string grouped this way means that the producer of the tuple decides which task of the consumer will receive this tuple. Direct groupings can only be declared on strings that have been declared as direct string. A bolt can get the task IDs of its consumers by either using the provided topology context or by keeping track of the output of the emit method in output collector. For partial key grouping, the stream is partitioned by the fields specified in the grouping, like the fields grouping, but are load balanced between two downstream bolts, which provides better utilization of resources when the incoming data is skewed. For non-grouping, well, this grouping specifies that you don't care about how the stream is grouped. Currently, non-groupings are equivalent to shuffle groupings. Eventually, though, streaming will push down bolts with non-groupings to execute in the same thread as the bolt or spout they subscribe from. Then let me introduce some key features of streaming. The Nimbus HA mechanism ensures continuous service processing even if one Nimbus is faulty, improving the cluster availability. It is implemented using the Zookeeper distributed lock. Leader election and active standby failover are based on the contention between the active Nimbus and the standby Nimbus. Besides, metadata is periodically synchronized between the active and standby Nimbus nodes to prevent topology data loss and the service interruption after active standby switch is performed. Disaster recovery, which we've seen before, it's a capability that services are automatically migrated from faulty nodes to normal ones, preventing service interruptions. For example, in this figure, if node 2 fails, the tasks will automatically transfer to node 1 and node 3 without manual operations. Streaming provides 3 levels of data reliability. At most once, the processed data may be lost, but it cannot be processed repeatedly. This reliability level offers the highest throughput. At least once, data may be processed repeatedly to ensure reliable data transmission. If response is not received within the specified time, the spout resends the data for processing. This reliability level may slightly affect system performance. And exactly once, data is successfully transmitted without loss, or redundancy processing. This reliability level offers the poorest performance. In actual application, selecting the reliability level is based on service requirements. For example, for the services requiring high data reliability, use the exactly once level to ensure that data is processed only once. For the services insensitive to data loss, use other levels to improve system performance. For the level at least once and exactly once, streaming has two kinds of processing mechanism, ACK and Trident. Let me explain the ACK mechanism in detail. A streaming topology has a set of special anchor tasks that track the DAG of tuples for every spell tuple. When an anchor sees that a DAG is complete, it sends a message to the spell task that created the spell tuple to act the message. You can set the number of anchor tasks for topology in the configuration. Streaming defaults topology anchors to one task per worker. The best way to understand streaming's reliability implementation is to look at the life cycle of tuples and tuple DAGs. When a tuple is created in a topology, whether in a spout or a bolt, it's given a random 64-bit ID. These IDs are used by anchors to check the tuple DAG for every spout tuple. Every tuple knows the IDs of all the spout tuples for which it exists in their tuple trees. When you emit a new tuple in a bolt, the spout tuple IDs from the tuple's anchors are copied into the new tuple. When a tuple is ACKed, it sends a message to the appropriate anchor tasks with information about how the tuple tree changed. In particular, it tells the anchor, I am now completed within the tree for this spout tuple, and there are the new tuples in the tree that were anchored to me. As mentioned already, you can have an arbitrary number of anchor tasks in a topology. This leads to the following question. When the tuple is ACKed in the topology, how does it know to which anchor task to send that information? Streaming uses mod hashing to map a spout tuple ID to an anchor task. Since every tuple carries with it the spout tuple IDs of all the trees they exist within, they know which anchor tasks to communicate with. If reliability isn't important to you, that is, you don't care about losing tuples in failure situations, then you can improve performance by not checking the tuple tree for spout tuples. Not checking a tuple tree reduces the number of messages transferred by half, since normally there is an ACK message for every tuple in the tuple tree. Additionally, it requires fewer IDs to be kept in each downstream tuple, reducing bandwidth usage. There are three ways to remove reliability. The first is to set config topology anchors to 0. In this case, streaming will call the ACK method on the spout immediately after the spout emits a tuple. The tuple tree won't be checked. The second way is to remove reliability on a message by message basis. You can turn off checking for an individual spout tuple by omitting a message ID in the spout output collector emit method. Finally, if you don't care if a particular subset of the tuple downstream in the topology failed to be processed, you can emit them as unanchored tuples. Since they are not anchored to any spout tuples, they won't cause any spout tuples to fail if they are not ACKed. Streaming provides a real-time distributed computing framework. It can obtain real-time messages from data sources such as Kafka, perform high throughput and low latency real-time computing on a real-time platform, and export results to message queues or implement data persistence to other components. Streaming is a computing platform and provides continuous query language in the service layer to facilitate service implementation. SQL is a SQL-like language used for real-time stream processing. Compared with SQL, SQL has introduced the concept of window, which allows data to be stored and processed in the memory. The SQL output is the computing results of data streams at a specific time. The user of SQL accelerates service development, enables tasks to be easily submitted to the streaming platform for real-time processing, facilitates output of results, and allows tasks to be terminated at the appropriate time. SQL has the following features. The SQL syntax is similar to the SQL syntax. Users who have basic knowledge of SQL can easily learn SQL and use SQL to develop services. In addition to basic expressions provided by SQL, SQL provides functions such as windows, filtering, and concurrency setting for stream processing. And SQL provides an extension interface to supporting increasingly complex service scenarios. Users can customize the input, output, serialization, and deserialization to meet specific service requirements. Besides, SQL provides detailed explanation of error codes, facilitating users to rectify faults. Here is the comparison of code between Storm and the Stream SQL. It's obvious that Stream SQL is much easier to use. And this is the architecture of Stream SQL. At the bottom is the computing engine, which usually refers to Storm or other stream processing engines. Stream and window here are built on stream processing engines and serve as the basis of all Stream SQL functions. Above stream and window are a collection of functional algorithms such as join, split, and merge. At the topmost layer are open query interfaces such as SQL or IDE. So this chapter briefly introduced streaming, like its definition, application scenarios, position infusion insight, and the system architecture and key features of streaming. Also introduce Stream SQL. Okay, that's all for streaming. Thank you.